Back for part 2 of our Joy with Polyatomic Ions. I know you're as excited as I am to watch this one as well. Hopefully you're not watching these two back to back or you're just going to fall asleep. So take a nap if you need to, go get a snack, come back and watch this in a minute. Anyway, so here we go. This is a little bit more detail about some of the polyatomic ions. I just figured it would be better to break this up into 2 parts as opposed to having it all in one because it's a little bit crazy. But just a little bit more information about kind of how they're organized or maybe some hints to memorize it. I'm not going to focus as much on writing names and formulas in here. We'll do more of that in class, but just some patterns. So a couple things here, just in general in terms of what a polyatomic ion is. One of the key ideas here is that they're very similar to molecules. The biggest difference, actually I say the biggest similarity, is the type of bonding that happens inside that polyatomic. They're all held together by shared electrons. So they're a little bit more tightly bonded than our other ions that we've dealt with before. A lot of times ionic compounds can dissolve in water. These polyatomics, when we dissolve them in water, they don't separate. They're stuck together because of that sharing relationship, those covalent bonds that are in there. So when we deal with them, because they're so tightly bonded, we always have to deal with them like they're a single unit. That's why they have one name. We don't call it nitrogen trioxide-ite or something like that. It's nitrate because it acts like a unit. It has a unit name for it. And that's a really important piece to kind of put in your pocket and try to memorize, try to remember as you're dealing with them, that they're a one thing even though they have a complex formula to them. What makes them different than molecules is that molecules by themselves are neutral. They're already balanced out inside the molecule. With these guys, these aren't balanced out. So even though they're pretty happy and they've shared, they had to have gained or lost some electrons somewhere. Most of these are anions, so most of them have gained an electron from something, or 2, or even 3 if it was phosphate, as opposed to ammonium, which gives one away. But they had to get one in there. So even though they're a group and they're bonded together happily, they're still ionically charged, and that's the key idea with those. And then because of that, they can now form electrostatic bonds, ionic bonds with other types of ions that are out there. So we indicate this by their names, that ATE and the ITE names that are found on most of our polyatomics. Again, there's a couple that don't have that, but most of them have that particular pattern. And again, now we can mix and match them. Just like any other ion, we could take any cation and any anion, stick it together. It's just now our anions are a little bit bigger and a little bit more complex than some of the anions that we dealt with in the past. So in terms of naming rules, again, I've mentioned this before in the past, that typically most of our anions are the same pattern where you've got a central atom and other ones that are kind of stuck to the outside. Typically we've got that ate and ite form. That central element to it, the nonmetal usually, is going to form the root of the name. So like these are chlorates or chlorite, based on that idea that chlorine's in the center. And then we use the ate and ite ending to deal with the number of atoms, oxygen, sorry, that are present. So in this case, with these two, chlorate has 3 oxygens and chlorite has 1 less oxygen, or 2. Doesn't change the form at least, or the charge at least, which is really, really nice. So if you know the charge of the chlorate, then you know it's a 1 minus. You know chlorite has 1 less oxygen but has the same charge, 1 minus. So sometimes it can help for you guys when you're memorizing to just remember the 8 forms and know that the ite forms are 1 less than that. It makes it a lot easier. And again, how is that happening? It has to do with the way the bond rearrangement's happening on the inside. They're forming some different sort of bonds between the oxygens or between the oxygen and the chlorines, just to make it stable in a slightly different arrangement to it. So it helps, again, if you're looking at this in terms of the idea of polyatomic ion families or oxyanion families. Almost all of them have an ate and an ite form, but some of them are even more extended than that, where you've got the ate and the ite form, but then there's one that has 1 more oxygen or even 1 less oxygen. And the chlorine family is the most complete one that I gave to you guys to learn that has all forms of this particular family. Bromine and iodine also do this as well, and you'll see those in a Chem 2 class, but I didn't cover them in our particular class. So again, the key idea here is the ate form is the basic one. Here it is up here in the top right. There's our chlorate, which is ClO3. The ate form is the most common form, or it's the kind of standard form if there's a whole family to it. The ITE form, which is over here, has 1 less oxygen than chlorate, and the hypochlorite form has 1 less even than that. So if chlorite has 2, hypochlorite would only have 1. So those are on the downside. We can also use ate and per as a prefix to tell me there's 1 more. So if chlorate's ClO3, then perchlorate is ClO4. It's got 1 additional oxygen to it, and that's what the per on the beginning stands for. So again, there's this whole sort of family thing that goes on with these, that you've got the base one, which is the ATE form, and then all these other 3 possible family members that have either -1, -2, or +1 oxygen to it. Does not change the charge at all. So that may help you with some of the other families that are on there. The 8 and the ite form are always the kind of the main form and then the one less form, but there may be that extended family that's there as well. And so again, not all of them have this, but some of them do, and this can help you kind of memorize that whole set of them as opposed to just trying to remember 4 different completely separate things. Here's some examples of them that are on there. Again, this particular table shows more than I'm asking you to remember for my class, although if you're watching this from a different class, you may have to memorize some of these as well. In any case, the ATE form is still considered to be the standard or the central form. The ITE form is always one less than the ATE form. So if there's only 2 present, like a lot of these, like nitrogen, sulfur, selenium, phosphorus, the ATE form has more, the ITE form has less. If there's only 1 form that's present, it's always called 8, like borate and carbonate. That's the only form that exists in nature, so that's how they name it. And then on the right, you've got those extended families that go from per-8 to 8 to ite to hypoite that has all 4 of the set down to them. So again, it's, if you see these extended families, there is a pattern to it that can help you kind of memorize what they are. Now, how do you remember what the oxygens are? That kind of becomes more of a tricky thing. There's a lot of different ways to do this. I've heard the 7 and the 4 is the kind of the method I've used. So here's what I mean by the 7 and the 4. Here's the outside 7. If you look at the ones that are in yellow here on this little periodic table, it almost looks like they're forming an outside 7, that shape, or an L shape if you want to. Those ones all have 3 oxygens to them. The biggest ones that you need to remember are carbonate and nitrate and chlorate. Those are the 3 of that group that have 3 oxygens to them. So again, it's that outside 7. On the inside, and there's sort of an orangish kind of color here on my screen, this is the 4, so it kind of looks like a 4 like this if you draw it like that. I don't know. But anyway, the inside one kind of looks like a 4. But the inside ones have 4 oxygens to them. And the big ones that you really need to know for my class are phosphate and sulfate. And then there's the other 2 that are actually the oxyanions that have a metal to them. So that's permanganate and chromate that also have 4 oxygens to it. If you look really closely at this particular diagram, you can hit pause. There's some patterns and charges too that, depending on how your mind works, may help you kind of remember how some of the charge patterns work. But it's definitely a lot more random looking than some of the other charge patterns that I've seen. So again, if it's on the outside, it's got 3 oxygens. If it's on the inside, it's got 4 oxygens. Or if it's the metal ones like chromate and permanganate, then it would also have 4 oxygens to it. So that's how I remember it. So there's a few of these, unfortunately, that are not systematically named, not just the 8-ite ones. These are not the oxyanions, so they can be a little bit frustrating. And a lot of these, it's because they've been known for so long. And so they were given names before we really even knew kind of how they were put together, so we didn't know there was a system. Anyway, so one of them is our cation, ammonium. Ammonium is related to the compound ammonia, and you may have heard of ammonia. It's really common in window cleaners, of all things, and they have a really similar form. So ammonium is that NH4 with a 1+ charge. So again, it's our only cation that we have to deal with. There's a couple others that are out there, but I didn't give them to you for this particular class. And then we've got some of the weird anions that are polyatomic, but they end in IDE. Remember, IDE is usually ending for monatomic ions, but there's some polyatomics that end in this. And again, these are ones that we've known about for a long time. So hydroxide, that one's kind of nice because it actually kind of tells you the name, hydrogen and oxygen. So that's kind of nice. Cyanide is definitely a weird one that definitely does not look like the name at all, but it's carbon and nitrogen bonded together to make a CN1- charge. And then peroxide. Now, peroxide's really weird. I'm going to do an example here in a second. Peroxide and oxide look very similar. Peroxide's a polyatomic because it's always 2 oxygens bonded together with a 2- charge. You've heard of hydrogen peroxide before versus hydrogen oxide. And again, they're different in terms of how they act. So let me give you an example of one. Here's sodium and oxide. Sodium and oxide look like this. It's a sodium ion and a single oxygen with a 2-. And our formula for that would be NaO. If I want to do sodium peroxide, peroxide is always 2 oxygens bonded together with a 2- charge. So this is what it looks like, and it looks really, really strange. And no, in this case, you would not reduce that down in order to make it NaO or something like that. Because peroxide is O2, you have to write it as O2, and then you balance the charge down to the Na2O2. And again, peroxide is different than oxygen gas because remember, oxygen gas is a molecule. It's O2, but with no charge to it. So again, peroxide's a tough one. You'll see that every once in a while, but it's kind of more of a challenging one to deal with. And now you can maybe see why the formula for hydrogen peroxide is H2O2 and not water, which is H2O. So anyway, there you go. A couple other ones here. Moving on, there are some kind of oxyanions that don't quite match some of the other systems, like acetate. I will always write acetate in its organic form, which is CH3COO as a 1- charge. If you use a different textbook, if you're looking stuff up online, you may see it written in the kind of compacted form, C2H3O2. They're both correct, so it doesn't really matter which one you use. But again, I tend to use the organic form because to me it's an organic molecule, so I write it out that way. A couple other ones that are a little bit weird. Dichromate doesn't tend to follow the pattern. It's kind of like a double chromate, except it's missing an oxygen, right? If CrO4 is chromate, dichromate should be Cr2O8, right? But it's not. Epic fail. So anyway, Cr2O7 is dichromate, so that's a little bit strange. We've got permanganate. So the element there is manganese and 4 oxygens, so to me, it almost follows the pattern of a manganate, but that particular thing, MnO3, doesn't exist, so they just go right to the MnO4 and call it permanganate. I didn't make it up. I don't know why they do that. There's also another set of families here that aren't the oxygen ions. They're hydrogen-containing ions. And you may have seen these. These are just based off of other ions, but with a hydrogen stuck on the front. The most common one is hydrogen carbonate. It's commonly called bicarbonate, and so you'll see both of those names back and forth. Either one is correct, and so you need to be able to be familiar with both. Baking soda is hydrogen carbonate. It's got a bicarbonate ion in there, sodium bicarbonate. The other ones that go into the same family, there's a hydrogen sulfate and there's a hydrogen phosphate as well. And again, we can call that bisulfate if you want to, but again, I'll typically call it hydrogen sulfate or hydrogen phosphate. The other one that you can get now, because phosphate is a 3-, and you can actually get a dihydrogen phosphate, which is an H2PO4. Keep in mind that every time you add a hydrogen to it, because hydrogens are +1, you do change the charge in this case. And so carbonate was a 2-, hydrogen carbonate's a 1-. Sulfate's a 2-, hydrogen sulfate is a 1-. So that may be a way to kind of help you remember what happens with those hydrogen-containing ions. There's a bunch of other ones that are out there too. I gave you a pretty limited list, so some of the biggies, but there's plenty of other crazy examples of polyatomics that are out there that are useful in different situations. So just, if you feel like you really just want to go nuts and memorize some other ones because you have nothing better to do today, there you go. There's a couple spares for you. Okay, so there you go. In terms of these, again, that basic idea, practice, practice, practice. Make sure that you've got your flashcards. Use your flashcards. Use them again. Use them a third time. When you're ready, turn them inside out. Make sure the name side is out, so then you're having to recall the formula. And if you're at part 2 here, maybe you're at that page. And then that's a lot more difficult. So seeing the word nitrate and knowing that it's NO3 is a lot harder than seeing the formula NO3 and knowing that it's nitrate. So again, practice using your flashcards, and then when you get to that point, turn them inside out. Again, keep in mind that pattern of the 8 and 8 family. That kind of makes it a little bit easier to memorize. Maybe just memorize the 8 forms, and then just know that the 8s is one less than those. Again, I gave you the pattern of the 3 8s and the 4 8s to keep in mind. There's the big ones that you need to know. That picture that was on that previous slide had a lot more than the ones that we use. So there's our big 7 that we have to deal with. There's 4 8s, and there's 3 3 8s. Maybe that'll help, maybe not. Again, keep in mind that with some of those extended families, specifically in the ones that I gave you with chlorine's family, that you do extend that ion family up to an extra one or to even subtracting one more. And then there's those ides, those weird ones like hydroxide, cyanide, and peroxide that are polyatomics but end in sort of a misleading name, and so you kind of have to watch out for those. Last but not least, don't forget you got to memorize those charges. I know that's a total pain. It just has to be done. So practice, practice, practice. Keep going, keep trying until you're like bleeding polyatomics. Then you know you're right. When it's just still like you're texting each other with polyatomic ions. You're like, hey, sulfate, go, and see who gets it. Then you're nerdy enough to be able to do well on this test. So good luck with that. I hope to see you in class. You better come to class, otherwise you're going to be in serious trouble. I'll know where you are. Have a good day.